Okay. Hello, guys. Welcome to week 12 lecture for this course. This is probably the last live session that I'll be taking. Aniket had already finished his doubt clearing session in the last week. And you guys have your exams on 29th of October. So hopefully you can refer to any of the live lecture sessions that we have done so far. If you have any doubts or, reach out to us via email if any issues are there. Anyhow, so in week 12, sir mainly focused on the introduction of partially observable Markov decision processes, and he mentioned one or two methods on what people use to solve the POM-DP problems. But he didn't go much into detail on the different methods that are available. There are more sophisticated and more heuristic based methods that are available to solve the POM DPs. But since sir didn't go deeper into that part, so I'll also just do a recap of what has been covered in week 12, and then we can finish the session for today. Okay, so yeah. So the before starting POM DP, the first question that one should probably ask is like, what is a Markov chain, right? So we are just going one step back and asking this question as in what is a Markov chain? So if I were to write down the definition of a Markov chain, so it has certain characteristics. Okay. So Markov chain has a finite number of discrete states, right? Second is that it also has the probabilities of transitions between states. This is another property. And third, and probably the most important property, is that the next state is only determined by current state. Okay, so this property is basically the crux of what Markov chain means. This is the Markov property. It says that the next state is only determined by whatever we have till the current state, and it doesn't assume any history of the previous state. It assumes that the information present in the current state is self-sufficient. So this is the Markov property. So this is what we mean by a Markov chain. Okay, so you have a bunch of discrete states. You know the probabilities of transition between each state, and then the next state is only determined by the current state, which is the Markov property. This is what is characteristics of a Markov chain, right? Similarly, if I go one step forward, there is something known as a hidden Markov model. Okay, so everything is or HMM. Okay, so everything is similar as that in the case of a Markov chain. You still have your finite number of discrete states. You still know the probabilities of transitions between each states, and also the next state is still determined by the current state itself. You obviously follow the Markov property, but the only issue is that we are unsure of which state we are in. Okay, so this is an additional constraint on a hidden Markov model. So you don't know the agent doesn't know the state in which the agent is currently at. So what the agent has access to is not the state directly, but some observation, a bunch of observation, and based on the observation, which is the sensory information that the agent has, it tries to make a guess or tries to build a belief of the state that it could currently be in. So you can say like the current state basically emits an observation. Okay. So this is the difference between a Markov chain and a hidden Markov model. Everything is same except that in a hidden Markov model, you have uh, an extra argument or an extra parameter, which we call as the observation. And based on the observation, we can access the state indirectly, but not a direct access, right? Now, okay, sorry. Okay, so now that we have defined Markov chain and the hidden Markov thing, we are moving one step forward, and then we move on to the POMDP part. So before POMDP, we now take a look at what is MDP. Okay, so MDP is basically an upgrade or some sort of an improvement of a Markov chain, and the improvement is basically on the control or the access that you have over the uh, model that is present. So again, if I were to jot down in an MDP or in a Markov decision process, you still have your finite number of discrete states. Again, you know the probabilities of transitions between states, and the controllable action in each state. So here you have an additional information. Uh, Apart from knowing the transition between each state, you also know the available actions that the agent has access to at each state. And the third point is that the next state is determined by current state and current action. So notice that this thing still doesn't violate the Markov property. This third point is still a Markov property, but the dependence, instead of being it only on the current state, it is getting extended to having a dependence on the current action as well. So this is the basic property of an MDP. And then an obvious improvement over it is the POMDP, which is the partially observable MDP. Right. Again, the 3 points are similar. And then the last point is we are unsure of which state we are in. Yeah. So far, what we have done is we have looked at 4 different types of models and how they differ. And if I were to make a distinction, so we have looked at 4 different type of Markov models. So if I were to make a distinction, I can represent this as, so these are all the Markov models that I have. Okay. Now, in these Markov models, I'm basically concerned about 2 changes or 2 different controls that the agent has, and based on that, we work with different Markov models. The first thing is, do we have control over state transitions? Okay, this is one differentiating parameter. And the second thing is that are states completely observable, right? So if you were to answer these questions, you would come up with the you would like come up with a need for these different Markov models. Okay, so if I were to write it, if this is no, this is yes, and this is no. Okay, so if I were to represent it, so if I don't have control over the state transitions, and if the states are completely observable, then this is a Markov chain, right? Secondly, if the states are still completely observable, but now I have control over the states. If this is a yes, then this is an MDP. Okay. Similarly, here, if I don't have control over the state transitions, but the states are also not visible. Okay. So the if both of them are no, so this is a hidden Markov model or an HMM. Lastly, if I have control over the state space and the states are not completely observable, so this is a POMDP. It's a partially observable MDP. So yeah, this is the differentiating factor in these four models that we have looked at. Okay. Now, okay, we'll quickly take a look at POMDP versus MDP. Okay, so we are trying to compare and contrast the differences or the advantages of one model, one Markov model over the other, right? So if I were to note this thing down, so for an MDP, what are the benefits? Okay, so the benefits I'll mention it with a plus sign. This is an obvious benefit. First, huge benefit that an MDP provides is that it's it's tractable to solve. Okay, so so far whatever we looked at, different methodologies, be it the value iteration method or the policy iteration method or any other MDP solving method, we know that an MDP is solvable, it's tractable to solve, and there exists a unique solution for a given MDP. Okay, so this is an obvious benefit. Second is that it is relatively easy to specify. If you remember, the MDP was basically a five tuple thing, right? So there was a state, then the action, you have the transition probabilities, the rewards, and the gamma, which is the discount factor. So the uh, MDP, what we have looked at was a five tuple, which consists of this things. And turns out that all these things are relatively easy to specify. So this is also an added bonus that an MDP provides. But the downside of it, or the negative part of it, is that it assumes perfect knowledge of states. So what it means is that at any given point of time, the agent should know with 100% accuracy the state it is currently at. Okay, it means that the agent always has some access to a global information wherein the state knowledge is you know encoded in the agent's memory. So any transition that the agent takes, it always knows what state it was before and what state it is currently at. Okay, so this is about MDP. Now let's go towards POMDP. So for POMDP, the first thing is that it treats all sources of uncertainty uniformly. What it means to say is that the observation that an agent makes in the environment, the observation is not 100% correct based on the sensory information that the agent has access to. So the sensors has some sort of a noise. The sensors are noisy by some percentage, and based on which the data that the sensor gives us is incorrect. Okay, so this noisiness in the sensors adds to uncertainty in the environment. So a POMDP basically treats all the sources of uncertainty uniformly. So think of it like this. Okay, so let's say you are uh, inside a car and you want to track the location. So what you do is you switch on the GPS, and then the GPS also has some uncertainty around it, right? It won't pinpoint the exact location you are at. It gives you a circular region. Mostly, the error is in terms of a few meters, and that is basically the uncertainty that is present in your positional estimate. Okay, so this uncertainty exists because it's not always possible to have a perfect knowledge of the states in the world around us. So noise in the information is a real and important parameter which needs to be taken care of. So POMDP treats all these sources of uncertainty uniformly. Second is that it allows for information gathering actions. Again, if you look at the MDP, whatever actions that the agent takes, the action is taken with the purpose of maximizing its objective function, right? But in the case of POMDP, turns out there are certain actions. If you take that certain action, it reduces the uncertainty in the environment. So the more information you gather about the environment, uh, the lesser is the uncertainty that you have about your current estimate. Okay, so any action that helps in updating or reducing your uncertainty is an important action. So this action is known as an action that is used for information gathering. So any exploratory action that you take that helps you gather some information, which in turn reduces the uncertainty in the environment. This is something that a POMDP model allows. Okay, so this is another benefit that a POMDP model provides. But the huge downside here is that it's hugely intractable to solve. The reason being that even though the number of states that you have is finite, but because of the noisiness around you, the uncertainty that you have is no longer a discrete quantity, but it can be considered as a continuous distribution. So since you're working on the beliefs rather than the states, so it's hugely intractable to solve a POMDP model optimally. So this is a negative point when it comes to POMDP, right? So this can be thought of as a broad perspective of what a POMDP model uh, contains. So there's an agent. The agent take actions in the world where the entire environment is the world plus the agent, and the environment, instead of returning the direct value of the next state, it basically returns some observations, right, which is based on the sensors that the agent has access to. And based on the observations, the agent basically updates its belief over the state it might probably be at, and accordingly the loop continues. Okay, so the goal here is selecting appropriate actions so that I want to maximize my objective function, whatever is that objective function. Okay, so now let's look at the formalism, okay, for a POMDP. So we'll formally define a POMDP. So in a POMDP model, what it consists of, right? So you have finite set of states, which is from S1 till Sn, belonging to the state space S. Then there is a finite set of actions. Again, you have a bunch of actions A1 to An belonging to the action space A. Then there is the probabilistic state action transitions, similar to what we had in the MDP. So this is P of S prime given A comma S. Then there is a reward for each state action pair, which is R of S comma A, which is the expected reward given as prime AS. Okay, again similar to what we had in the MDP part. The new addition here is there is a finite set of observations. So observations O1 to On belonging to the set of observation space omega. And then there is a conditional observation probability. Okay. So this is your uh, this is the conditional probability in which you view the observation. So you can think of it like it, this as a function which maps the set of state space, action space, and the observation space into a probability distribution. So given a particular state, what is the probability you make observation O? This is the basic definition. Once you define all this, you can define the POM-DP model. So your POM-DP, let's call it as a. So I'll call my POM-DP as P. So this basically is a 7 tuple. So in your MDP was a 5 tuple. So POM-DP is basically a 7 tuple. The first thing is the state space, then the action space, the probability transitions, and the set of observation space. Then you have the rewards, and this is the conditional observation probability, and lastly gamma, which is the discount parameter. Okay, so this is form DP tuple, right? So this is the formal definition of a form DP model. Next up, which is important, is something called the belief state. Okay, so here so far we know that the agents don't have direct access to the state space. Rather, they have access to observations by means of the sensors which the agents have. So if you're a human being, your sensors are your eyes, ears, skin, and other stuff. So you use that sensors to basically improve your understanding of what you're currently at, right? Okay. So if we look at the belief state, so the belief state is basically it's a probability distribution over the world states. So my belief bell of S, this bell of S is the belief state space is equal to the probability of the probability distribution over all the world states. Okay. And second thing, the belief gets updated over time. So based on the actions that you take and based on the observations that you make, you're constantly updating the belief that you have. Okay. So the belief state has two main update rules. First is the action update rule. Okay. How it works is, so my new belief, well, So my new belief, my Bell prime of S prime, okay, is equal to the marginal sum. Sorry. So my Bell prime S prime is equal to the marginal sum over all the state space capital S. Then I take all the state probabilities and just simply multiply it with the belief at the current state. Okay. So the action update rule tells me that I'm effectively for each action that I'm taking. So that action is fixed. Okay. So the action here is fixed. So for each action that I'm taking a marginal sum over. It's a marginal sum over the belief state that I have, and this is summed over all the states in the state space. And based on that, I come up with my Bell prime S prime. So S prime is basically the new state that I'll be in after taking action A, right? Second thing is that second thing is the observation update rule. Okay. Again, earlier this was a marginal summation over the transition probability. So you can probably figure out. So in this case, it is again going to be a marginal sum, but not over the transition probability, but rather on the conditional observation probability. Okay. So we have two different probability distributions. First is the transition probability. Second is the observation probability. So this is basically just summed over the observation probability. Rather not summed. It's just a multiplication over that. Okay. The belief and the observations are two independent quantities. So uh, they are independent. They are independent quantities. So it's just a direct product of that. So my Bell prime of S is simply my probability of observation, probability of taking observation, having observation O given state S multiplied by my belief over state S. Okay, so this is the update when I make an observation O uh, at state S, right? So this is the observation update rule. So this all are the formalisms for a POMDP model. So next, maybe we'll motivate or understand the POMDP problem better by means of some examples. Okay, so maybe we can take 5-10 minutes in understanding what this example is and how the belief gets updated. Okay, so this is a simple problem. It's a tiger example. So basically, there's a game that you're playing. So in the game, there are two doors. There is a door on the left. There is a door on the right. So behind one door, there is a tiger, and behind another door, there is a treasure. Okay. So you have to correctly select the door in which there is a treasure. And if you select the door which has a tiger, you get a huge negative penalty. And you don't know a priori what exactly each door contains, because there's a 50-50 chance of each door containing either the tiger or the treasure. Okay. So the observation that the agent has access to is basically you can hear the sound of the tiger. So you can put your ear and hear what is behind the left door. So if you hear the growl of the tiger, so you can say that there is a tiger on the left door. And similarly, if you uh, observe or hear the right side door, you can similarly predict if there is a tiger or not. But again, note that this observation is not 100% accurate. There is noisiness in whatever hearing that you're doing. So, so the reward function we'll look. So for penalty for wrong opening is -100. If you open the door and there's a tiger behind it, you get a reward of -100. And a reward for opening the correct door is +10. And the cost for listening action is -1. So for each action that you take, so the action is basically whether I want to make an observation on the left door or on the right door. So each action has a corresponding cost. So for each time step or for each action that you take to listen, to invoke the observation, it has a cost of -1. Okay. So the actions here are either listen, zeroth action is listen, first action is open left, second action is open right. Okay. So you have two states, S0 and S1. So S0 state in the uh, blue oval over here is also called as the tiger left state. Okay. So here the probability of observation that tiger is on the left, given that I'm listening at state S0 is 0.85. So with 85% accuracy, you can say that the tiger is on the left if you observe T of L when you're listening at state S0. And there is a 15% error with which you can make a misprediction. Okay. And similarly, state S1 on the green bubble over here, this is also called as tiger right, or TR. So again, probability of observation that T of R given I'm listening state S1 is 0.85, and the other way around is 0.15. Okay. So this is the simple tiger example. So so this is how the belief state basically gets updated. So the probability of S0 versus S1 being true, being the true underlying state that you have access to. So initially you have a 50-50 belief. So the probability of state S0 and the probability of state S1 is 0.5 because you have no prior information or no prior knowledge about what is behind each door. And for each trial, the tiger and the treasure gets randomly reset. So the initial belief is 50-50. So this is how the initial belief looks like. Yeah. So upon listening, the belief state should change according to the Bayesian update, which is the filtering which is happening over here. So if you you know do make an observation T of L. Okay, T of L means you make an observation that tiger is on the left. Now basically the belief state is shifting to the left, towards the left door. So you're saying after making observation P of L that the tiger is on the left, that I hear the tiger noises on the left side, I can say with 85% probability that the tiger is on the left and the treasure, and with 15% probability, I can say that the tiger is not on the left side. Okay, so this is how the belief shifts when I'm making one observation. So the cost to make that observation is -1, right? So your cost to listen is -1. Similarly, if I make the observation that the tiger is on the right, that's how my belief state shifts. Okay. Now the right question here you want to ask is, given this is the belief state, okay, given that I have made an observation and that I know I can say with 85 the door I open will have the tiger or not. Okay, so will you open that door or not? Okay, it's a matter of the risk that the agent is willing to take, right? Otherwise, what you can do is, if you don't want to open the left or the right door, you again listen. So again, listening this thing basically reinforces your belief. If basically the first time you heard that the tiger is on the left, so you want to listen again. If the second time also you hear that the tiger is coming from the left, so your belief state shifts further to the left. Okay, so this is how the belief state gets formed. Okay, so just take a look at this slide. So again, the tiger example. So the policy pi is a map basically from 0 to 1, which is listen, open, uh, listen, open left, and open right. So 0, 1 is basically the state space, and listen, open left, and open right is the action. So the policy pi is basically a map from the states to the action. So what should the policy be? Be that listen until sure and then open. But where I cut off? Okay, so the tiger optimal policy for T is this. So this is how the belief looks like. Okay, so if the first time I did this listen part, and then listen basically tells me that 90% chance the tiger is on the right side. Okay. So so this is how my belief shifts. Okay. Okay. Note that here this is basically the PDF and this is the cumulative distribution. Okay. So that's why these are all summed up to one. So you just take a look at the oh no, wait. Yeah, okay. So this is how the optimal policy looks like, right? So okay, so this is basically the state. Okay, so you have three actions: listen, left, and right. So the thing is, if you sorry, can erase this thing. Okay, so you have three actions: left, listen, and right. And based on that, you make beliefs on the states. Okay. So if you take action, which is listen. Okay. Sorry, if you take action that open left. Wait. Okay, maybe we just ignore the numbers for now because this is also confusing me right now as I look into it. Okay, think of it like this. So the first time you listen, your the probabilities between the three actions, split. So the probability of taking uh, different action gets split equivalent to the observation that you make. So this is the optimal policy for time t equal to 1. Now, if I want to look at the optimal policy for time t equal to 2, that means I want to take two observations. And if I take two observations, so now I have uh, five different states and with different probabilities. Okay, so this is how my belief keeps on shifting towards different part. So initial belief was that the tiger is behind either the left door or the right door, but with increasing number of observations, I am gathering more and more information, and based on that, I'm reinforcing my belief. Okay, so this was the tiger example. Another similar example is something known as the dark light domain. Okay, so here it's a simple navigation problem. Okay, so should the agent starts from the start position and needs to go to the goal. But the thing is, when the agent is in the dark part, it doesn't know where the agent is. Okay, so unless it goes to the light region, which is this white line over here. So the closer the agent gets to the white region, the agent gets complete knowledge of the state or its current location. Imagine it's similar to basically you trying to navigate in a room which is dark. Okay, and if there is some source of light, you basically try to move closer and closer to that source of light so that you have a good enough estimate of where I want to go, and based on that you start moving in that direction. Okay, so if you look at this circle over here, so this circle is basically the uncertainty, which is modeled as a Gaussian distribution. Okay, so the reason for modeling uncertainty as a Gaussian distribution is because uh, it's beneficial because it's a unimodal distribution, and it basically holds true in many real life applications. Okay, so the yellow dot over here is basically the mean of the Gaussian, and the bigger circle around it is the covariance around it. Okay, and basically you want to try to navigate from the start to the goal. If there was no light or dark domain, the optimal policy is basically go like this. Okay, but because we have a constraint on the observability, that means we can observe better if we move to the light region. So here the policy kind of takes this kind of a turn. So here if you see, as I'm moving closer and closer to the light source, the covariance around me is slowly decreasing, right? And when I reach this particular region, I have the minimum possible. I have the least uncertainty in my position. Okay, And then once I have that, I have a good enough estimate of the belief that I want. And based on the strong belief that I have, I try to take action in the towards the goal direction. Okay. And then the agent starts moving towards the goal direction. And then you see as the agent moves further away from the light, the uncertainty starts growing by some small amount. Okay. So the longer time the agent stays away from the light source, the uncertainty in its position keeps on growing. So this is the dark light domain. So hopefully this gives you an intuition of the usefulness of POM-DP model. Another important application to look at is basically this car landmark thing. Okay, so sometimes what happens is when you're trying to do autonomous driving in an uncertain environment. Okay, so the uncertainty comes from the part that you don't have access to a global positioning system. So there is no an, uh, GPS available to you. So the car tries to basically wander aimlessly because it has no means of localizing itself, because the car doesn't know the current position of which it is at, right? So if the car has less information about its position, then any action that it takes, basically, you know, the error basically keeps on accumulating, right? So the covariance sort of increases. So here there are two landmarks which are circled by the which have this green circle. So this landmarks are can be thought of as some other moving vehicles or some obstacles which can also move. So if the car goes closer to these landmarks, then it gets like uh, as the car moves closer to the landmark, then it gets a better understanding, or it can accurately localize itself. Okay, so this is the problem of the vehicle localization. So the closer you move to these landmarks, which acts as beacons, right? So this can be thought of as some sort of a beacon. So if you go closer to that landmark or closer to that obstacle, you basically can accurately localize yourself. Okay, so this is how the graph looks like. So if the car wanders aimlessly, so over here you see there is a huge uncertainty in the final position of the car. Rather, if the car takes this sort of a direction, it has less uncertainty. Here, the obstacles are static. Okay, and if the obstacles are also moving, so you see the closer the car is to the obstacle, the lower is the uncertainty it has in its current position. So this is uh, a very important problem in cooperative localization. So people in controls, they a lot of research is going on how to basically improve this part. So these type of problems typically make use of POM-DP models, right? Now, I'll just quickly discuss what Sir has covered in class regarding solving MDPs. So he has mentioned four different methods. One is the history-based methods. Second is QMDP. Third is the direct POM-DP method, and fourth is by using predictive state representation. I won't go into much detail of what was there in the last two methods, because even Sir didn't go much into detail of what was there. So what we'll do is we'll briefly discuss the two methods, the first two methods that Sir covered, and after that we can call it a day. So we take a look at history-based methods, right? So what happens in history-based methods is, so here you don't have access to a belief state. So you don't have a belief that you keep updating with each action or each observation that you make, but rather what you do is you store a history of all the states and actions that you have encountered so far, and after that you make an update. So note that here in this history-based method, okay, I should write this. So here, let's say your Q function. So if this is the observation and this is the action you took, So this is maintained in the history. So I should draw the environment. So this is the same environment that sir had used. So if this is basically a room, this is a wall. Okay. Now, you know, I just discretize this into grid cells. So here the agent won't know the exact position of or the exact row column in which it currently is at, but rather it has access to basically uh, the four perpendicular neighboring cells. So this is the north, east, the north grid cell, east grid cell, south grid cell, and west grid cell. And the observation is basically a clockwise representation. So if there's an obstacle, you represent it by 1. Otherwise, you represent it by 0, right? So here you see this state, this state, this state, and this state. All of them uh, will have the same observation. That is, no, sorry. Uh, okay, I can say that this state and this state will have the same observation, meaning that since the obstacle is present to the north and south in both these cells, so you can say that both these states will have the same observation. Now, since the observation is same, now how do you differentiate between what state I'm currently at? Okay, and similarly over here also, imagine that beyond the wall is also an obstacle. Okay, so if there is nothing above, it's also considered an obstacle because you can't traverse into that region, right? So this all will have the same observation. Now, based on that, you want to make a prediction on which state I'm currently at, and by the same logic, all these states will also have the same observation, assuming that whatever is outside the wall is also an obstacle, right? So what you're doing in history-based methods is you're basically trying to append whatever observations that you're getting and whatever actions you're taking. Okay, so this is what we do in the first step, and the second step is you. So here what it says is that I have taken two upward actions and I'm still getting the same observation in both the cases. Or rather, I should remove this. So I'm getting the same observation in both the cases. So now what, how to basically determine my states. Okay. And similarly, if I take another action, what are the observations I make and uh, what is the probability with which I can pinpoint my current state. Okay. So maybe you guys should refer back to the lectures because sir had very clearly mentioned this problem, the uh, state pinpointing part by the example in a proper manner. So I'm just giving a recap. Okay. So turns out that this history-based methods basically what it says is that it still assumes the Markov property. Okay, but instead of a first order Markov property, this assumes a kth order. It assumes a kth order Markov model. Okay, and the k that you select uh, is basically a parameter that the user defines, and based on the accuracy with which you select the k in the environment that you have, you get uh, you get basically uh, the results of on solving the MDP. Okay, so I'm just describing the method. I mean the different approaches, but I won't go deep into how these are actually solved. Even sir didn't cover that, so I'm just giving a brief overview. Okay, so it turns out there are some issues with this method. Three main issues. First is that the state space becomes huge. Okay, because imagine if you have a million states in the POM DP setting, and you're trying to do a history based method, so in which you are appending the states, so the state space becomes humongous in this case, right? This is a problem of large state space. Second is unequal uh, state description. So basically, when I'm trying to do the queue update on the state space, so the size of the state space keeps increasing based on the history that has been accumulated so far. So the state description is unequal. And next part is it's leads to a wastage of computation. Okay. These are three main issues with these history-based methods. I won't go into the detail of why that is so. That wasn't covered also in the class. Okay, we'll just take a look at the second method, which is the QMDP-like method, right? So what you do is, in the POM DP, assume that the POM DP is known. From the POM DP, you basically extract the MDP path and you solve the MDP. Okay. So what you're doing is your first step you do is you solve the underlying MDP in the POM DP part. And second thing that you do is once you have solved the MDP, you just execute it, right? But the problem comes here is that execution is still a problem. Why? Because the agent doesn't have access to the MDP. The agent is basically accessing the POM DP, right? So you don't have access to the states, but the observation. So here the execution is still a problem in this case. So how do you deal with this? So in order to deal with the execution part, so what you're trying to do is you take the Q values for a state action pair and you multiply it with the belief for state as at that you multiply the belief at that given state. Okay, and once you do that, you sum it over all the states. Sum it over all the states in the state space, and then what you get here, you call it as Q bel of S comma A. So this is an updated Q function that you're maintaining in the MDP while you're maintaining the Q of S comma A. Here, what you're doing is you're just summing it over the belief over the states, and what you get is the Q bel of S comma A. Now, yeah. So before that, you understand that why this is a problem. Execution is a problem because the problem that you have solved, the MDP that you have solved, is by assuming that you have a state knowledge. This is a big assumption that you made in solving the MDP. And then basically what you're doing is you're using some sort of a heuristic to convert into execution policy. So because of this thing, the policy that we execute based on the MDP that we have learned so far might not be optimal. Okay, so this is something important that one should keep in mind. And once you have this Q bel of S comma A, so the policy pi is simply the argmax of A over Q of bel S comma A. Okay. So this is the second method for this QM solutions for this QMDP like methods. Okay. Yeah, I think with this we conclude what has been covered in the lecture so far. maybe we can just quickly solve the assignment problems. I think Aniket already covered two questions in the assignment problem. So uh, I'll just quickly do a recap and look at the solution. Okay, so suppose we solve an MDP using QMDP-like solution. We assume MDP is known and solve it to learn Q values. Which of the following is true? So for QMDP, like we discussed, we can recover a policy in the POMDP environment by weighing the Q values by the belief distribution, so that pi of S is argmax of this Belus times QS of A. Okay, just what we saw in the last slide. Okay, here it's an assertion reasoning based question. So it says that the black squares are the obstacles, white squares are the traversable regions. Agents can only see one step in the four cardinal directions, and the agent's observations are always correct, 100% correct. There is no prior information given the states. So the assertion is that if the observation is that there are no obstacles to the east or west, but are present to the north and south, the belief that the agent is in the green shaded square is zero 0.5. Okay, so it's saying if I only have obstacles on the north and on the south, so being on the green state is zero 0.5. The reason is only green and blue shades have obstructions in the north south, but not the east and west. So this is incorrect because here you can clearly see this state also has north south obstruction, but not on the east west. So the probability is changed. So here both the assertion and the reasoning are false. Now this thing Aniket had already covered in last week's session. So here you have this kind of an obstacle, this kind of a grid. So the gray are the obstacles, white is the traversable region. So the agent can only sense in the four cardinal directions. Here the sensor has a 90% accuracy. So the agent can, so the sensor can uh, correctly sense an obstacle with 90% accuracy and given error 10% of the time. So given that the agent senses no obstacles in any direction, which is probability that I'm in state S, given that the agent senses no obstacles. So this thing, so how you define it? So since this is a conditional probability, you would do probability of being in state X. Uh, sorry. So you do this probability of being in uh, state capital X, intersection of probability of making observation 0, 0, 0. But since both are independent, right? So I can just multiply this thing. And then divided by this quantity. So this is basically the sum of uh, basically the sum of being in each individual state and making observation 0, 0, 0, 0. Okay. So if you just write it down, this thing becomes 1 by 5 because you can randomly drop in any of the 5 states with probability 1 by 5. And here the probability of making observation 0, 0, 0, 0 is 0.9 power 4 because there is actually no obstacle in each direction and the sensor can make the observation with 90% probability. That's why divided by. So you just add this. In each of the state, you see that I shouldn't sense obstacle in any direction, but in all the above four cells, there are obstacles in two directions. So in that case, like I need to ensure that two of my sensors misfire. So in those 4 by 5 states, I have two sensors giving me the correct reading and two sensors misfiring and giving me the incorrect reading. So if you just substitute this thing and put in the values, okay, I don't remember the solution. Uh, Let me see. Yeah, so in this case, this you would end up with this answer. Okay, so you can just put in the values. I just referred to this answer and just ticked it. Now, similarly, in the same environment as before, what is the probability that agent was not dropped in cell marked X if observation is that obstacles are present only to the north and south? So the observation is that obstacles are present to the north and south, and agent is not at cell X. So similarly, you can simply again do probability of being here, making observation 1 0 1 0. So this is the probability of making observation, having obstacles on the north south and being in state X. You do the whole computation, and then in the end you just do 1 minus this, 1 minus this probability, because uh, this is a probability that agent was not dropped into cell mark text. So if you do the whole calculation, you get this answer. And lastly, in partially observable systems, histories that both include the sequence of observation and the sequence of actions are typically able to disambiguate the true state of an agent better than the histories that only include the sequence of observation. This is the assertion. And the reasoning is that the different sequence of actions can lead to different interpretation of the sequence of sensor observations. Okay. So here, both the assertion is true, because uh, having information about the sequence of actions is better to disambiguate the true state rather than having only the sequence of observation. And the reasoning they have given is that different sequence of actions can lead to different interpretations of the sequence of the sensor observations. So here, both the assertion and the reason both corroborate each other, hence, and they are both true. So here, this is the correct answer for this question. Okay. Yeah, I think with this, we can conclude week 12 lecture. Uh, so this would be the last live session class for this semester from my end and for this course as a whole. So if you guys would be interested, if you liked what you have studied so far in RL, probably the next course you want to look at is something known as deep reinforcement learning. Okay. So this course basically needs you to have done one course on RL as a prerequisite. So this is a course. Uh, it's an online course basically. It's offered by UC Berkeley. It's available free, and it's taken by Professor Sergey Levine. Okay. So this is if you want to explore more about reinforcement learning, and if you are further interested to learn about the current practical application, be it the autonomous driving car, or the AlphaGo player beating the world, the AlphaGo machine beating the Go champion. So these typically employ deep reinforcement learning methods. So you can, and I think if you are interested, you should take a look at this course. So, and yeah, you can also have access to all the tutorial sessions and the Python codes that they have uh, done as part of the course. So there are a bunch of assignments you can do. So this is free of cost. You just need to uh, make a Google search. You can access to all the course content. I think with the pandemic, the classes were conducted in an online fashion. So this is available for free. Okay. So do check this out if you are interested. So I think we can wrap up for today. What we have covered in this course so far. So thank you for attending. I hope you do well in your exam, and have a nice day. Okay, I'll see you then. Bye.